Solar is by far the most abundant source of energy we have on Earth. But the real challenge is turning this energy into useful work. Plants have already mastered this task in the form of photosynthesis, converting sunlight to sugar. While we can't match nature's millions of years of experience, humans have come up with some pretty cool ways to harness the sun's energy productively. Especially in recent years, we have been putting more effort into finding alternatives to our major source of energy for the last 2 centuries: fossil fuels. This video takes a peek at some of the major ways in which humans are working on using the sun's rays to meet our increasing demands. Keep in mind that there may be other technologies out there too, including those that have not yet been discovered. Solar technologies are often divided into 2 groups: solar thermal and photovoltaic. The idea behind solar thermal is simple. It is to convert sunlight to heat. This heat is turned into mechanical energy, which can then be turned into electricity using a generator. The most common way for this to be implemented is by heating up water until it boils, creating steam. The expansion of water into steam drives a turbine, which is connected to a generator, which gives us electricity. This is the same mechanism that is used in coal power plants, but instead of burning coal for heat, it uses reflected, concentrated sunlight. A famous example of solar thermal is Solar 2, a concentrated solar power site in Southern California. Mirrors that track the sun, or heliostats, are used to concentrate sunlight onto a centralized tower. Rather than directly heating up water to create steam, Solar 2 heats up a tank of molten salt that stores the heat until it is used. This allows the plant to continue operating up to 3 hours after the sun sets. Steam turbine technology is the same technology used to generate about 80% of the world's electricity. Modern steam turbines are very efficient, having benefited from over a century of R&D. Some newer solar thermal plants use Stirling engines, high-efficiency engines that are powered by the temperature difference between a hot and cold reservoir. It is important to note that solar thermal plants become more effective as they become larger. Also, energy is lost to the environment during the conversion of sunlight to thermal and then mechanical energy. A key metric in evaluating energy production methods is dollar per watt installed capacity. But remember to be skeptical of figures because relevant details are often left out. For example, shouldn't we consider the cost of building the site? Or the cost of transporting the raw materials to the site? Or the cost of extracting the raw materials from the earth? In any case, for solar thermal technologies, this buck per watt figure varies dramatically depending on such factors as land prices, intensity of sunlight, and weather conditions. For example, Andasol 1, a concentrated solar power site in southern Spain, costs $8.67 per watt installed capacity, whereas another concentrated solar power site, Cloncurry Solar Power Station in Australia, is projected to cost only $3.13 per watt. Photovoltaics, or PVs, form the second branch of electricity generating solar technologies. Unlike solar thermal, PVs convert the sun's energy directly to electricity without the intermediate steps of thermal or mechanical energy. Let's begin by briefly exploring how a particular type of solar cell works. PV cells are made of semiconductor materials, most typically silicon. A large single crystal of pure silicon forms the starting point for the monocrystalline silicon solar cell, the most efficient type in common use. A defining characteristic of silicon is its diamond cubic crystal structure, which you see here. Each silicon atom shares all of the 4 electrons in its outermost electron shell with 4 neighbors. So we have 4 covalent bonds per atom. Let's switch to a 2-dimensional view of this structure. In this state, each silicon atom's valence electrons are tightly constrained by covalent bonds, shown in green. But an external source of energy, such as light, can break these bonds, freeing an electron to migrate through the lattice. Since electrons are negatively charged, The broken bond, represented by a dotted line, has a positive charge. This can be thought of as an imaginary, positively charged particle that we will call a hole. Now, imagine a second electron that is broken free somewhere else in the lattice. It is quite likely to jump into the vacant spot left by the first electron, restoring the original broken bond, but leaving a new broken bond behind. Thus, the hole has moved and can keep moving throughout the crystal. Now, a pure silicon crystal is quite a good insulator, but as the word semiconductor suggests, it can also be made to act similarly to a conductor. This happens through what is called doping. By adding even a tiny amount of atoms of another element to the silicon, we can change the amount of charge carriers, electrons and holes, in the crystal while maintaining its electrical neutrality. An element commonly used for this is boron. Boron only has 3 valence electrons versus silicon's 4, and can thus only form full bonds with 3 neighboring silicon atoms. Thus, each boron atom introduces a hole into the crystal. Because of all the extra positively charged holes, silicon doped with boron is called p-type. Phosphorus, on the other hand, has 5 valence electrons. Because only 4 can bond with neighboring silicon atoms, the extra electron is weakly bound and can easily be enticed away. Therefore, silicon doped with phosphorus has plenty of negatively charged, free-moving electrons and is referred to as n-type. Note that there is no charge on p or n-type silicon, but each has a lot of charge carriers, the holes or electrons, that are free to move rather than locked in the crystal structure. These free charge carriers give the silicon some conductive properties. The magic happens when we take p and n-type silicon and join them together. The result is a photovoltaic cell. Let's look at why exactly this happens in such p-n junctions. When p and n-type are initially joined, all of the free holes are on the p side, and all of the free electrons are on the n side. Both segments of the silicon are still electrically neutral. As the holes on the p side and free electrons on the n side move through the crystal structure, they meet up and cancel out. The area at the center of the junction now has a perfect crystalline structure, just as if it were an undoped pure silicon crystal. Because there are no longer any holes or free electrons in this area, it is called the depletion region. A consequence of there being no charge carriers is that the depletion region is an insulator, just as pure silicon is an insulator. Now consider what happened when the holes and free electrons met up to make the depletion region. The p-type, which was originally electrically neutral with extra holes, lost its holes when they met up with the free electrons from the n-type. The p-type, therefore, has lost positively charged particles near the depletion region, and is therefore gone from neutrally charged to negatively charged. By the same reasoning, the n-type has become positively charged near the depletion region. Of course, these sketches are simply illustrations. In reality, the depletion region is much wider than 2 rows of atoms. Now, remember that a photon of sufficient energy can break one of these bonds to form a new electron-hole pair. If this happens near the depletion region, the newly created electron-hole pair will split, with the electron moving to the positively charged n-type silicon, and the hole moving to the negatively charged p-type. Now, this is a little tricky. Remember, the n-type silicon is named for its extra electron charge carriers, not because it is negatively charged. So you can, in fact, have a positively charged n-type region. The same holds true for the now negatively charged p-type region. Now that our electron-hole pair has split up, we have a separation of charge. The more photons that hit the p-n junction, the more electron-hole pairs are created, and the more charge is separated. Therefore, electrons build up on the n side of the p-n junction, and holes build up on the p side. If you connect the P and N sides of the junction with a wire, the electrons will travel through the wire to meet the holes. Now we have current, which is proportional to the amount of sunlight hitting the cell. So this is how a photovoltaic cell fundamentally works. Light separates a charge in the cell, which flows through a circuit. Single crystal silicon is the most commonly used material in PV cells due to its high efficiency. However, there are many ways to achieve the photovoltaic effect. Polycrystalline silicon, in the form of a thin film, is also used by spreading a thin coating onto a cheap base, such as plastic or glass. Other semiconductors besides silicon can also be used to make cells, and there are even cells that use light-sensitive dyes to supply the electron-hole pairs that create current. In the last few years, global PV installations have been increasing at over 30% annually. Germany has been leading the charge, in no small part thanks to high feed-in tariffs. And how does the buck per watt figure match up for PV? Again, it's tough to find numbers that everyone agrees on, but to throw some out there, APS, the largest electric utility in Arizona, recently estimated that the cost of installing PV within the state is around $6 per watt. This includes a government incentive of $2.30 per watt. In contrast, SolarBuzz.com keeps track of a solar module price index, which gives a price per peak installed watt for PV modules in the US. As of March 2011, the index placed PV module price at $3.19 per watt. These are still young technologies, in that they only contribute marginally to global electricity production. As we see them implemented on increasing scales, we will see what challenges they face and hopefully how to overcome these. Governments will have a key role to play here, both with subsidies and with how easy they make it to obtain the permits to bring such technologies into action. So we hope you take the time to learn more about these electricity-generating solar technologies, as well as other renewable energy production methods. While some are more high-profile, others don't get the attention they deserve. Learn more about them, and find your own way to get us all on a path of growth through sustainable energy.